Alright, hey AP Chemistry. So this is the last video on quick checks. There'll be more videos, probably more practice problems. I may do some of your textbook exercises. I may also even do some AP style questions and practice test questions for tomorrow. But this video is going to focus on chemical bonding, wrapping up, connecting molecular polarity, and going back to calculating bond energies that I had showed you in a previous video. Referring to your electronegativity handout, which was this one. Now, this is, again, in the Google Classroom. So I'm looking at these electronegativities here. Consider the molecule BF3. The BF bond is classified as ionic, polar covalent, or nonpolar covalent. So if I'm looking at BF, the electronegativity of boron is 2, and the electronegativity of fluorine is 4. So En is 2, En is 4, delta En is 2. And according to that, if it is about 2, it's supposed to be ionic, but in this case, it's going to be polar covalent. Delta X greater than 1.6 makes it polar covalent. 2 is on the low end of the ionic side, so we're just going to say that just from experimental data, I know that BF is a polar covalent bond. So this is polar covalent. Now I'm showing you some harder examples to differentiate. So in the case of two nonmetals, they're going to be covalently bonded. If this was like Na and F, and the difference in electronegativity was about 2, if that had happened, or something like Be and F, then I would go a little bit more borderline ionic. In most cases, it'll be easier to spell out what their differences. So since the delta N is about 2, we're going to make this polar covalent. We're going to write the dipoles. Remember, dipole is going to go from less electronegative to more electronegative. And again, the way dipoles work is it's kind of like how the electrons are moving or who's pulling on the electrons. The arrow goes to the element that really wants to hold on to electrons, and the line is the starting place of where the electrons are coming from. So the way that I'm going to draw this molecule is by drawing the dipoles, and all of the dipoles go away from the boron, giving the boron kind of a slight delta plus, and each of those fluorines have a delta minus. Remember, the delta minus is the more electronegative element, and the delta plus is the less electronegative element. And remember the trends in electronegativity. Electronegativity increases as you go from left to right, and it increases as you go from bottom to top. So if I was just looking at this, I would know that between boron and fluorine, since they're in the same row, fluorine would definitely have a higher electronegativity than boron. Additionally, fluorine is the most electronegative element. So we always use examples of fluorine because there is no way you can tell who is more electronegative because it's fluorine. All right. Now, based on Vesper theory, what shape would you assign to the molecule BF3? BF3 has no lone pairs in the center atom. So going back to my previous video, B is a central atom. It has 3 electron domains, or we call that things. It has 3 things around the central atom with no lone pairs. This is going to be trigonal planar. Also, the BF3 has sp2 hybridized orbitals. There are 3 things, so I need 3 letters. SPP. 3 things, 3 letters. So, in trying to figure out whether this molecule is polar or nonpolar, I gotta look at the dipoles. The dipoles, I'm gonna use a different color on the prettier molecule I drew over here. The dipoles are going all in opposite directions. But they're going in opposite directions, and they're going to be canceling each other out. They cancel out. And this has to do with vector sums. If any of you have ever taken physics or even math, the vector of the pole going this way is actually equal to the vector of both these fluorines going on an angle. Now, how do I do that, or what am I going to do for AP Chemistry? For the scope of this course, typically if I have a symmetrical molecule like this, where if I rotate this molecule, it looks all the same, and there's no lone pairs in the central atom, if I have dipoles going in opposite directions, it's going to cancel out. So this molecule is going to be nonpolar. And so my reasoning are that dipoles will cancel out. All right, and I've mentioned this in a previous video, but it's kind of like you're traveling, right? And you go 3 blocks to the left, and then you go 3 blocks to the right. Where are you? Back at the starting point, right? So this is kind of like, oh, I went up the block around the corner. Well, it's the same thing as going diagonally to that same position, right? So I don't know if that analogy is helpful, but the way dipoles work is if there's an overall net dipole, let's say I was doing HF, right? There is one direction, delta plus, delta minus. This is definitely polar. There's only one direction. If I have something like CO2 though, there's a direction this way, and then a direction going in the complete opposite way. This is going to be nonpolar, and we should know that CO2 is definitely a nonpolar molecule. So this is an example of polar versus nonpolar. If I have these dipoles, or if I have this pulling going in opposite direction, it's going to end up being nonpolar. If I have the pulling going in one direction, it's going to be superpolar. And what's pulling, I mean, electrons are being taken or held onto tighter by the element that's more electronegative. And we mentioned either in class or in an earlier video that electronegativity really depends on subatomic structure and protons and effective nuclear charge. Okay? Now the bottom of this video kind of recalls back to section 9.10. I wanted to go over this again because the previous video was kind of short and I was going to have a part 2, but I'll consider this a part 2. Part 2 was going to talk about how we connected using Hess's law, but I decided, for the scope of what you're learning at home, just focus on using bond energies. So we have to balance this equation. So N2, one N here, so let's put 2 here. That gives me 6 H's, so I need 3 H's here. And now I'm balanced, okay? Now remember, if I want to calculate bond energy, it's the number of bonds broken, which are my reactant bonds, minus the number of bonds formed, which are my product bonds. Okay? So if I want to kind of draw some Lewis structures here, from some prior knowledge, I know that N2 looks like this. And each H2 looks like this. So I'm going to draw all 3 H2s. And then NH3, and there's 2 of them, look like this. And you could follow Lewis structure rules to draw out all your structures. So bonds broken, I need to break an N double bond N bond, which I can figure that out. It's right here, N double bond N. I have to break an N double bond N bond, and I have to break 3 H2 bonds. Okay? So bonds broken, N2 and the 3 H2s. What energy is that associated with? Well, 945 kilojoules per mole plus 3 times 436 kilojoules per mole. And I'm sorry that that's getting squished into my structure, but I'm adding the energy of the N2 and 3 of the H2s. And then bonds formed. Well, all together it looks like I made 1, 2, 3, 4, 5, 6 NH bonds are formed. So if I want a bond between an N and H, that's 391. So it's going to be 6 times 391 kilojoules per mole. All right? And so now the math that's involved in here, I'm going to do this math on the side. I have to do 945 plus 3 times 436. Okay, because that was the energy for the HH. And that's equal to 2,253 kilojoules per mole. That's the energy required to break all the bonds in the reactants. We calculate the energy of the bonds in the reactants because that's the energy that we're starting with all of these initial reactants. I have to break all of these bonds in order for them to form our products. And then the energy of the products is going to be 6 times 391. That's because, again, I made 1 NH, 2 NH, 3 NH, 4, 5, 6 NH bonds because I made 2 NH3s. So if I do that, I'm going to do 6 times 391, and that's equal to 2346 kilojoules per mole. And the way that I do delta HF, it's going to be a difference or a subtraction between these two, right? The amount of energy of the bonds broken, or the reactant bonds, minus the product bonds that are formed. So 2253 minus 2346, and I get negative 93 kilojoules per mole for delta F of this reaction. And this reaction is going to be exothermic. How do I know it's exothermic? If delta H is equal to negative, energy must be released. And that means that it's exothermic. Okay? So I'm hoping that this quick check was a helpful review of doing, again, shapes, hybridization, and talking about polarity or polar bonds, and then going back to calculating bond energies and getting the overall delta H of the reaction using the bond energies. And just to quickly recap here, I always do the subtraction of all of the bond energies of the reactants from all of the bond energies of the products. And you have to draw out structures, because if you didn't, you wouldn't know what bonds would be present. So that's why we relearn about how to draw Lewis structures in order to do such calculations like so. Okay? All right. So I'm hoping these quick checks were helpful. Let me know if you still have any other burning questions or concerns, or what's still circling in your mind about how to draw Lewis structures, how to give me the shape or the hybridization, and then eventually calculate bond energies and look at molecular polarity. Those are the big 3 topics that you needed for knowing in chapters 9 and 10 for over this break. All right, any questions or concerns, let me know in the Google Classroom or in the Remind.